Alright, so today we are going to be continuing our discussion about surfaces, and specifically we're going to be talking about surfaces and friction. Alright, so today we're talking about surfaces, and we're going to be talking about the properties of surfaces, the most common properties, and we're going to be talking about the mechanism of friction and how it relates to material properties. As you probably are aware of, when we talk about machines or machine surfaces, there's an awful lot of parts that have machined or ground surfaces, and this makes up this is, I would say, I don't know what the actual percentages are, but it's a majority of surfaces are either machined or ground for most machines. The other types of surfaces that we see in machine parts are commonly cast or forged, but it's less common for these types of surfaces to be in contact with one another. All surfaces, just like all surfaces have cracks from a fatigue perspective, we can also say that all surfaces are rough, or they have a roughness associated with them, or have an associated roughness. Okay, and depending on the application, rough is a word that is a qualitative word. So a rough surface in one application may be a very smooth surface in another context, and the roughness of a surface is directly related to the finishing process used in the surface, or the finishing process used on the surface. Okay, so often you'll get machine parts that are then thrown into a deburring machine or tumbling machine for hours with different media, or they're ground with different types of grinding. They all produce surface roughness. Now, surfaces and surface roughness are both qualitatively and quantitatively inspected. They're often qualitatively and quantitatively inspected. We can use qualitative visual inspection with a comparator. Okay, and so if you search, you can find comparators for pretty cheap. You can find them at usually less than $150. You can find them at places like MSC, for example. This is a surface comparator. So basically you would take this comparator and you would look at the surface, and you can compare it. So for example, between turning and milling, horizontal milling, vertical milling, lapping, reaming, you get different measures of surfaces. So you can look at what process you have, and you can just look at how the surface appears, and then you can go over and get your estimated RA value, and then you can compare that to what the specification might be. Okay, so you can usually get these for pretty cheap. You can put them in your toolbox, and you can get a feel for, based on the process, you can match how the surface looks to the comparator. Okay, but in order for them to get those numbers, they have to actually have quantitative data, and that quantitative data usually comes from profilometer. Okay, and the profilometer is used to measure the actual surface roughness. Okay, and in this case, we have to really define, well, what are we really talking about when we talk about surface roughness? What is the surface roughness? And profilometer is a device, and there's different types of profilometers. This is a Mitutoyo. Mitutoyo makes precision instruments, as well as Marv, Ferrell. And basically, you have a stylus. You put this on the surface. It will look something sort of like this graphic here. And the stylus is dragged across the surface, and the displacement of the tip is measured. And if the tip is really small, and the forces that cause it to go up and down are pretty small, and the profilometer will measure the roughness of the surface. And the roughness of the surface obviously is going to be filtered somewhat by how big the diameter of the tip is. Okay, so these are profilometers you can buy if you need actual metrology data associated with part that you're making. So sometimes you have to also, they'll do a call out for a drawing will do a call out on a component that has a requirement in surface roughness. So maybe the person that's machining it or manufacturing, they can look at the optical comparator and they can say, okay, this looks right. And then every so many parts, they might have to actually measure with the profilometer and make sure they're still in spec. All right. So if you have a surface, and surface looks like this, and you have a profilometer, you have your little profilometer tip, and say you have a nice round tip, then as you drag the tip over the surface, it's going to rise and fall along these edges, and you're going to get data. If you're measuring this vertical displacement, you're going to get some data that will look like this. Okay, and typically the size of the stylus is on the order of about 0.5 microns or micrometers, and the changes in height can be on the order of about 0.125. Can measure changes in height of about 0.25 microns. So that would be this would be our height resolution. Okay, and this would be your sort of the radius. Okay, so what this means is that you can't really measure features such as this, that would be less than, the radius of the tip, and the sensitivity of the profilometer in the vertical direction is about 0.125 microns, which is pretty small. So you can get pretty good measurements using these devices. But we still haven't really talked about, well, what is surface roughness? Okay, so if you say a surface has, this roughness versus that roughness, what are we really talking about? Well, it turns out that there's standards that define how we measure surface roughness. Okay, and we're going to talk about the two most common ones. In fact, the ISO, or the International Organization for Standards, has 19 different standard statistical measures of surfaces. Are statistical measures for surface roughness. Okay, so we're going to talk about the most common measures of surface. Okay, so these will be the most common surface roughness measures, and these are RA and RQ. So RA is the average of the absolute value of the measured points, and we can write RA. RA is equal to 1 over LM, and if you have a surface that you're measuring, and this is taken from your book, and it shows some of the most common surface metrics. Okay, these are the 7 of the 16 different ones, and we're going to talk about RA and RQ here, but LM is the length of the evaluated surface that you're looking at, and then the RA or RQ metric is the Y metric, and each point is the Y height for that surface. And so the RA values are 1 over the length of the evaluated surface integrated over the surface if we take the absolute value of each point in the data set. And this is also the arithmetic mean. And we also have the discrete version of it. Okay, so this is your definition, and when we actually take data, we actually have discretized data points, and this is our discrete version of RA, and the discrete version is simply the arithmetic mean, which is 1 over n times the sum of the points from I equal 1 to n, times the absolute value of yi. Okay, and this would be your ith point. Alright, so that's RA, and if we want to compare sort of what the RA values might look like from a profilometer, you can take a look. This is another image taken from your book. This is a ground surface, and this is a machine surface, and you can get a feel for this. Is something that might be an output from a profilometer. So you would drag the stylus across the surface, and then it would spit out these different statistical measures of the surface as defined in this standard. Okay. So we have RA. RA is commonly used. The other one that is commonly used is RQ. And RQ is the root mean square of the average or we'll just call it the RMS value, or root mean square value. And the root mean square, the definition is just the square root of 1 over the evaluated surface over the integral from 0 to the length of the surface. You take the squared height of each value in that surface, and we also have the discrete version, because that's the version that we actually use when we would calculate this if we had the raw profilometer data, and that is simply just the 1 over n. This is our RQ. It's 1 over n times the sum of I equals 1 to n yi squared, and then this is square root. Okay. So some interesting things is that if a surface has a so go back up here. Let's say if the surface has a Gaussian distribution, then the RQ value is the same as the standard deviation. Okay, so assuming you have a Gaussian surface distribution, basically that you have a Gaussian distribution of surface roughness over the mean. If you were to look at the surface roughness of this and you had a nice Gaussian distribution, then the RQ value is the same thing as the standard deviation of the surface, which gives you the statistical confidence of where your values are in the surface. And if, for example, for a sinusoidal distribution, okay, the relationship, excuse me, sorry about that. The relationship between RA And RQ is RQ over RA is equal to pi over 2 root 2, which is 1.11. And the point here is that RQ is slightly about 11% greater than RA. Okay, so if you're measuring something and you need an RQ value and you measure RA, you could actually make a mistake in your quality control. Okay, and this has happened. It happens all the time. And this is just for illustration. This is this is for a sinusoidal distribution. Okay. We're just using a certain distribution as an example. So the point here is not that RQ over RA is equal to 1.11. The point is that RQ is often slightly larger for some statistical surface distributions than RA. Okay, so that's the basic way of looking at surfaces, and we can also take a look at what are some of the most common values for surface roughness for some common surfaces. Excuse me. Okay, and so we can take a look here, and this shows us that based upon the different manufacturing processes, we can get different values of RA. In this case, this is the RA value, and this is the surface roughness in microns or in microinches. This is sort of like your standard process. So if you were to order a sand casting from a company, this is kind of what you would expect to get back from them. This is your output for forming. Okay, so this is kind of like you're getting the raw material. And as you can see, we have the different methods. If we want really, really high surface finishes, then we need to most commonly post-process the surface. Okay, so we have your casting, forming, machining, and then down here, these would be your finishing processes. Okay, so where you're polishing, you're lacting, electropolishing, etc. And that would be sort of like getting down here into your small RA values here with these post-processing methods. Okay. So if we talk about machine elements and we think about what are the surface roughnesses of various machine elements, we can get a feel for them as well right here. Okay, so if we're looking at gears, gears are usually made by hobbing, which is a machining process, and we naturally would expect that we'd be able to get a surface roughness out that's within the range of a machined and ground surface. And we have journal bearings, plain bearings, and other bearing elements, and you can get a feel for what surface roughness is necessary that people get the life that they need to get out of these different components. So it's a pretty useful graph. And this book was taken from Schmid's book, Design of Machine Elements.